Welcome. This is yet another in my series of updates of Solar Cycles 25 activity. I'm doing this not by month but by Carrington rotation. A Carrington rotation is one complete rotation of the Sun with respect to the Earth. And this is Carrington rotation 2251 that covers the date from the 18th of November to the 15th of December. First, let's summarize the general status of the Sun. You'll remember that the solar minimum was defined as December 2019. That would be Carrington rotation 2225. So we're now 2 years into solar cycle 25. That's 26 Carrington rotations. The typical time to maximum is about 53 months or 57 Carrington rotations. So we've got quite a way to go. In fact, we're about 46% of the way to maximum. The interesting thing is that the solar B angle, that's the nod of the polar axis towards or away from the Earth, at the moment it's close to 0, so we're seeing the Sun basically at its equator. And that's useful for a number of reasons. The most useful aspect of this is that we can use the polar coronal holes to judge where we are in the solar cycle. The polar coronal holes are at maximum extent during solar minimum, as you can see here from this picture on the right. The two polar coronal holes here are well defined and large. In fact, there's not much activity on the Sun in general. At solar maximum, they disappear as seen here. Thus, so we can use the extent of the polar coronal holes to judge where we are in the solar cycle. So let's do that now. On the left here, I have the northern polar coronal hole taken at 1 week intervals, either side of the B angle being 0. As you can see, the northern polar coronal hole is mostly well defined. On the right, however, we have the southern polar coronal hole. It doesn't seem to be quite so well defined. It seems to be a little smaller. But then again, there is some emission between us and the polar coronal hole in the first figure. So I think these aren't too far off being similar. But both holes are still present, and both holes are quite large. So that means we're in the early stages of the solar cycle. There's some years to go before these will disappear. So how is solar cycle 25 doing so far? The sunspot number is clearly increasing faster than it did for solar cycle 24. You can see the minimum here between solar cycles 24 and 25 here in December of 2019. And since then, the number of sunspots has grown steadily. If you compare that with the equivalent period back in the previous cycle, this is a much more rapid rise. They're also increasing faster than the official NOAA forecast. This implies that solar maximum will either be earlier or bigger than the previous cycle, or of course both. So are we heading to a grand solar minimum? We certainly aren't at the moment. There's no indication of that. So let's take a look at the evolution of the sunspot number throughout the period of Carrington rotation 2251. That's here, marked with the blue arrow. You'll note that there are at least 3 days marked on the official record at being 0 sunspot number. Now I take issue with that because on 2 of those days I distinctly saw sunspots on the Sun. Here on the 9th there were 2 sunspots just south of Sun center, and on the 11th there was a new set of sunspots coming over the east limb in the northern hemisphere. Yet they're counted as 0 sunspots. So we really only had 1 0 sunspot day during this period. I'm particularly interested by the difference between the northern and southern hemispheres. Here we mark the sunspot number as a function of time, differentiating between the northern and southern hemisphere. Green here says there's an excess of northern hemisphere sunspots. Red indicates there's an excess of southern hemisphere sunspots. For most of these cycles, you can see that north has led the rise phase of these cycles, and the southern hemisphere has dominated the decay phase of these cycles. The notable exception is solar cycle 19, where it was basically all northern hemisphere. Now, our cycle 25 at the moment is showing something rather strange. It's already being dominated by the southern hemisphere. And the only thing that's vaguely equivalent to this is the very beginning of solar cycle 22. Not quite sure what to make of that yet, except for to say it implies that this cycle is going to be different from some of the previous ones. So let's take a detailed look at Carrington rotation 2251. To do that, we're going to look at the series of videos from the SDO, HMI and AIA instruments. The speed of these videos is about 1 second per day, so they're very much speeded up. We'll start at the cool surface area and work to higher altitudes and higher temperatures. Each layer has something different to teach us. To do that, we're going to look at a series of movies. We're going to start with the optical images. That's the same wavelength that our eyes can see. And we see the bright photosphere at about 5700 degrees Kelvin. Sunspots are somewhat cooler at 4700 degrees Kelvin and so appear darker. Note how they emerge, evolve and spread and dissipate over time. Sunspots are magnetic features, so we want to take a look at the magnetic field, and to do that we use magnetograms from the SDO HMI instruments. Sunspots are cooler because of those magnetic fields poking through the photosphere, causing less energy to escape from their vicinity. Magnetic fields are present all over the sun, not just at the location of sunspots. Note that the magnetic regions are in pairs, balance of positive and negative magnetic fields, shown by the white and the black on these images. Next, we'll move higher in the solar atmosphere, both in altitude and in temperature. To do that, we're going to use the AIA helium-2 at 304 channel. Its effective temperature is about 50,000 degrees. So we're in a transition region from about 5,700 degrees at the surface of the sun up to over 1 million degrees at the corona. And so temperatures are changing very rapidly through this region, and densities are dropping equally rapidly to maintain pressure balance. Next, we move up to the low temperature corona. And we are looking at the iron 9 line at 171 angstroms. The effective temperature is about 630,000 degrees Kelvin. And we're looking for large-scale magnetic loops within and between active regions, sunspots in other words. Now we go into the so-called quiet corona that is actually not all that quiet. To do that, we're going to look at the iron 12 line at 193 angstroms. The effective temperature here is about 1.2 million degrees Kelvin. You're looking for dynamics here. If you look over the whole area, everything seems to be changing continuously. There are dark areas here, like the one in the top left of this image, which are coronal holes. These are open magnetic field lines where high-speed coronal winds spread out into the solar system, and they can cause geomagnetic storms if one of those should hit Earth. Now we're going to look at the corona above sunspots. These are called active regions. These are the bright areas you see in this image. We're looking at the iron 16 line at 335 angstroms. The temperature here is about 2.5 million degrees Kelvin. We're looking for the formation and flaring in new regions as they form on the disk. Last but not least, we're going to take a look at some flares, and to do that we're going to look at the iron 18 line at 94 angstroms. The temperature here is about 6.3 million degrees Kelvin, and we're looking for flashes in the active regions. Every flash is a flare. The bigger the flash, the bigger the flare. I don't know how many flares you thought you saw in that series, but going over the full 28 days from the GOES X-ray instrument, there were 50 C flares, there was 1 M flare, and no X flares. So let's take a look at that 1 M flare. The M flare occurred at 6:58 on the 5th of December, and it was an M1.4 flare. That makes it the 19th largest flare of solar cycle 25 so far. And it was from region 2898, which has just gone over the southwest limb. So it actually probably was a bit larger flare than what they classified it as. And you can see, as far as the size with respect to the Earth, it is massive. There were also a lot of other fairly large flares during that period of time, but they were just C flares. So let's take a look at the movie of that flare. Next, we'll take a look at coronal mass ejections, and there we have to go to a different spacecraft and a different instrument. We're going to the SOHO spacecraft and the LASCO coronagraphs on there, the C2 and the C3. The C2 field of view is the red field of view in the middle. The sun is about the size of that blue disk I've shown in this image, and the blue area on the outside is the larger, lower resolution C3 field of view. Look for eruptions off the limbs in any direction, and look for comets. I didn't see any, but you might be sharper eyed than I am. We only had one geomagnetic storm during this period. It was on the 30th November. You can see here it was a low-level geomagnetic storm. That means that it was a G1 event with Kp of equal to 5. There were some disturbed periods of the magnetosphere for the following day, but we never got back to geomagnetic storm level. So all in all, solar activity had decreased from the previous rotation. We had 3 official spotless days, though I dispute that somewhat. Solar cycle 25 is rising about 20% faster than solar cycle 24. Solar maximum is likely to be either larger and or earlier than forecasted by NOAA and NASA. But what I didn't mention in this, and I'll be doing a special video on it, is what came in the next few days. Take a look at this X-ray plot. You can see just after this period ended, we had a whole bunch of flares. We've had over 100 C flares and 5 M flares in that period. And so I'm going to go into this period in more detail once it has ended. So until next time, stay safe and keep well. Goodbye.